All right, so last time we talked about 11.1 sequences, and there was also a supplemental video available. So um, today we're going to start on series, which builds off of sequences. So hopefully that material is pretty solid for you on sequences. We're going to be building on that today on series. The quote of the day today is from Peter Arve, the co-founder of Prezi, the presentation software. Um, And his quote is, "The concept of always being reachable makes us present nowhere." Um, and I think this is an important thing today, right? We have these wonderful little devices in our pocket that at the press of a few buttons, we can pretty much learn anything that we want to learn or, accomplish very many things very quickly and efficiently. But at the same time, it kind of seems like there's always an expectation that we're checking our email all the time or getting back to texts all the time or that we're always reachable, and it makes it really hard for us to be sometimes present with the folks that we're actually physically in the room with, or we might be on social media or um, playing games or whatever it may be on the phone. So this is certainly something that I struggle with, and I think everybody struggles with these days. So I think it's a good reminder from time to time, especially um, with our spring break coming up in a few weeks. Maybe planning to take a little bit of that time and disconnect a little bit. The thing that made me think about this was my wife and I were hanging out with a couple of friends over the weekend, and they were talking about that they were planning to just kind of go up to a cabin and next weekend and just kind of disconnect from everything, have like a uh, time away from their cell phones. And their daughter is actually doing a uh, cell phone fast for Lent. Like she bought a dumb phone, like a literal flip phone, and she put away her smartphone and she's only using her dumb phone for I guess from now until Easter to try to just disconnect from it a little bit. So that's what made me think of this idea. Okay, so remember that a sequence is really just essentially an infinitely long list of elements or terms. So what is a series? 11.2. A series, roughly speaking, is the sum of a sequence or the sum of the elements of a sequence. We'll see there's a little more nuance to it than that, which we'll see throughout chapter 11, but this is a pretty good characterization of a series. In other words, if I consider a sequence, A1, A2, A3, A4, etc., and I just add those terms up, or those elements up this way, if I make those elements terms of a sum, A1 plus A2 plus A3 plus A4, and so on, I can write that in the more succinct notation using sigma notation, capital sigma, uh, this little symbol there. I equals 1 to infinity, A sub I. So we have sum, we just say sum, I equals 1 to infinity. The increment here is assumed to be just 1 unit. So 1, 2, 3, 4, 5 as we're stepping through, A sub I. So I say sum, I equals 1 to infinity, A sub I. So this is a series. So for instance, I'm going to come back to this in just a second here. So for instance, a series might look like something like this. Sum I equals 1 to infinity of 1 over 2 to the I. When I equals 1, this is 1 over 2 to the 1, or 1/2. That's the first term. To that, we're going to add the I equals 2 term, 1 over 2 to the 2, or 1/4. And to that, we're going to add the I equals 3 term, 1 over 2 cubed, or 8, and the I equals 4 term, and so on forever. We would call this a series. A very important idea related to series is the idea of the partial sum. The nth partial sum is the sum of the first n terms of a series. So if I add b1, b2, b3 up through bn, we could write that as the sum I equals 1 to n, not to infinity, but to n, bi. This would be the nth partial sum of the series b1, b2, b3 forever, or sum I equals 1 to infinity, bi. this sum I equals 1 to n, bi would be the nth partial sum of that series. And we might refer to it as something like s subscript n. So for instance, down here we had our series, sum 1 over 2 to the I, sum I equals 1 to infinity, 1 over 2 to the I to be clear. 1/2 plus a fourth plus an eighth plus a 16th forever. That's a series. However, sum I equals 1 to 5, 1 over 2 to the I, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 32, end of story, nothing else. We would call that the fifth partial sum of the series because it goes up to term 5. Something we might note is, so this would be like S5. S1 is going to be 1/2. S2 is going to be 1/2 plus 1/4. S3, 1/2 plus 1/4 plus 1/8, and so on. In other words, if I add on one more term of the series, I have one more term on my partial sum. It's the next partial sum. What's the next partial sum after S2? It's S3. That sounds a lot like a sequence, right? If I plug in 1, I get some output in the real numbers, 1/2. If I plug in 2, I get another output, 1/2 plus 1/4. If I plug in 3, I get another output. It sounds like a function, takes inputs and yields outputs, whose domain is the natural numbers, 1, 2, 3, 4, 5. These SNs are actually a sequence. So I can talk about the sequence of partial sums. And let me actually zoom this in a little bit. I have some extra space here, make it a little easier for you to see. So this is actually the sequence of partial sums. Super important idea in series. And unfortunately, kind of series and sequence, like they start with S, they sound a little bit the same, they're related concepts. It's easy to get them to get aspects of each one conflated with the other. So that's why I said, ideally you'll have practiced a bit with sequences, kind of have that vocabulary and those ideas, fairly well down. And now when we move to series, that'll help keep these ideas a bit separate. So when we have a series, the infinitely many terms added together, related to that series, we have partial sums, and we have a first partial sum, just the first term, a second partial sum, which is the sum of the first two terms, right? The second partial sum is not just the second term of the series. The second partial sum is the first term plus the second term. The third partial sum is the sum of the first three terms of the series, and so on. This makes a sequence of partial sums, S1, S2, S3, S4, etc. Now this is a sequence of partial sums, but it's a sequence, so it has the same properties of sequences that we talked about last time. Specifically, this sequence, it might or might not converge. We might be interested in asking, does this sequence, 1/2, 3, 4, 7, 8, 15, 16, and so on, does this particular sequence converge? As n goes to infinity, does this essentially get closer and closer to some real number and stay close to that number? Now, something you might be asking yourself is, well, let's just kind of take an aside here for a second. If I'm adding up infinitely many things, I mean, if I'm adding up infinitely many things, isn't this going to like just shoot off to infinity or something? And the answer is not necessarily. And I think at this point we can see this a little more clearly than maybe earlier in the semester. But we know that there are integrals, improper integrals, that have an infinite domain, like, maybe integral from 1 to infinity of something like 1 over x squared, where we're in essence adding up like positive Riemann boxes, positive area Riemann boxes, infinitely many of them, but they get small enough, fast enough that they actually integrate to a real number. And then of course there are examples where that doesn't happen, where the the function gets small, but it doesn't quite get small enough fast enough, or maybe where the function doesn't get small at all, and it obviously doesn't converge. So these series, when I add together infinitely many things, uh, it might that there might be a sensible sum for that series, or it might not be a sensible thing to say that if I add up all these things, it equals some real number. How do we discriminate between those two cases? Well, we see we have infinities floating around here. And as I mentioned in the improper integral section, anytime we have infinities floating around, that this is kind of an analog of an infinite domain to our improper integral, right? Anytime we have these infinities floating around, we have to be very precise with our definitions and really stick to our definitions. There are paradoxical things that happen here. And I want to caution you that, if you go on YouTube and you look up, I don't know, facts about series or something like that, probably some of the top videos to be recommended to you will be things that, from the perspective of this course, we would say are incorrect. So there's the famous, I think it's like 1 plus 2 plus 3 plus 4 forever equals like negative 112. And there's like a number file video on that, and, very reputable sources, YouTubers that, are saying this and making this claim. And if you're not paying very, very close attention to what they're saying, or certainly if you just read the headline and go with it, you're going to have a fundamental misunderstanding. It's not necessarily that their statement is incorrect, but it's something like working under a different set of assumptions than we're working with in this course. So from the perspective of this course and the definitions and assumptions we're making, it would be incorrect. There actually is a mathologer video. There's a guy, his channel's mathologer. He's a math professor and he does very good videos. I really like his videos. I recommend basically anything that he puts out there. He kind of takes a complicated concept and tries to break it down at several different levels and kind of build it up so that basically no matter what level you're at in your mathematical journey, you'll probably get something out of it. You'll probably probably have a step or two you're like, oh yeah, I kind of understand that easily. Maybe a step where it's like, oh, that's a bit of a refresher, and then a step where it's like I learned something new, and then maybe another step or two where it's maybe a bit above your head, but that's fine. You can catch it wherever you're at along that journey. So he has one, I think he posted it a few years ago, maybe 2 years ago or so now, I'd guess, where he kind of breaks that apart carefully and really explains everything really well. But anyway, so just a cautionary statement, and there will be another cautionary statement, or maybe 12 throughout this chapter 11, that we just have to be very careful, because we're messing about with infinities here, and sometimes our intuition deceives us, and we have to be careful to obey the rules and the definitions that we are working under. So we have a definition. This is a definition that we are choosing. We're saying this is what this means. This is the definition for convergence of a series. If I want to be able to write, this equals 4 or something like that, this is what I would mean by such a statement. Given a series, given some I equals 1 to infinity of a sub I, let Sn, S sub n, denote the nth partial sum. That is, S sub n equals some I equals 1 to n, a sub I. As a side note, it's important to note that each partial sum individually is just, you're maybe adding up 5 things or 10 things, maybe you're even adding up 50 million things, but it's just a finite number of things added up. So all of our nice properties, like the associative property of addition and the commutative property of addition, all of that works perfectly nicely here. We can use any of that kind of stuff for factoring stuff out, anything like that on the partial sums. We just have a finite number of things added together. So just a side note there. So given a series AI and Sn, the nth partial sum of the series, consider the sequence of partial sums, the sequence Sn, S1, S2, S3, S4, adding one term, adding up the first 2 terms, adding up the first 3 terms, adding up the first 4 terms, and kind of building up the series in that manner, if this sequence of partial sums is convergent, that is, we would say if Sn goes to S, a real number, if our sequence of partial sums converges to a real number, then we say the series is said to be convergent. And furthermore, we say that the sum of the series is S, and that the value of the series is just the same as S. So for instance, if we look at our series up here, sum I equals 1 to infinity 1 over 2 to the I, 1/2 plus a fourth plus eighth plus 16th and so on. If I look at my partial sums, the first one being 1/2, half plus a quarter is 3/4, half plus a quarter plus an eighth, 7/8. It kind of looks like 2 to the n on the bottom, right? 2, 4, 8, 16, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and then 1 less than that in the numerator. It looks like 2 to the n subtract 1 over 2 to the n. It looks like that's the formula for, say, Sn. Or it looks like that's 1 minus 1 over 2 to the n. It kind of feels like this sequence of partial sums is heading toward 1. We can make an argument, and I think I've shown this argument more than once in this class, at least between this class and Calc 1 before. We can make an argument that if we take a whole piece of pizza or a whole pizza or something like that, and we cut off half of it, and then 1/4 is half of what's left, and 1/8 is half of what's left, and 1/16 is again half of what's left. So we just get, 1/16 plus 1/16 would be everything, and I can split this 1/16 into 1/32 plus 1/32, half of what's left, and then keep doing that, keep splitting off what's left. Seems like it should be equal to 1. If I look at these numbers down here, it seems like they're heading toward 1. The sequence of partial sums seems to be converging to 1. And if my intuition is correct, if I have a formula for the sequence of partial sums as 1 minus 1 over 2 to the n, I can see as n goes to infinity, this does go to 1. 1 over 2 to the n goes to 0, and we're just left with 1. So does it seem plausible? I would say yes. Can we prove it carefully? We're going to work on that. That is going to be what we're going to discuss down here with geometric series. So, to be continued for that part. But it does seem plausible. It seems reasonable that under this definition, we can look at series, and, at least for this series, it seems like a series can converge to a number. It does seem like I can write sum I equals 1 to infinity, 1 over 2 to the I equals 1. And I'm not tricking you here. This will actually be true. So, it does seem plausible. It seems like that would work. And in this case, our intuition is leading us in the correct direction. Right. So we have a definition, and under this definition, we can actually evaluate the value of this series. These infinitely many things added together, we would say that their sum is 1 for this particular series as a sum of 1. Okay, let's look at a theorem. This theorem is called the test for divergence. So kind of a little bit of foreshadowing or whatever it may be. Some series like this one are quite nice, and we can decide their convergence properties pretty easily, and even if they converge, figure out what their sum is pretty easily. Occasionally that happens. Quite often, if we have a series, we can't really easily tell whether it converges just based on the definition, or if we can tell it converges, it's often difficult to tell what its sum is, or to write its sum in kind of a closed form expression. So as a result, we have a bunch of theorems, a bunch of tests for series. I say, here's a series. The most basic thing we want to know about it is, does it converge? If it doesn't converge, it makes no sense to even look for a sum for it. So the most basic thing I want to ask is, this series, does it converge? And most series, it's not as straightforward as what we looked at up here, just kind of writing out a formula for the sequence of partial sums and figuring out what happens. So we have a bunch of tests for series. And this is our first convergence test for series, and it's called the test for divergence, or sometimes called the criterion for divergence. And the statement is this, that if the individual terms in the series, if these, like up here, they were 1/2, 1/4, 1/8, 1/16, if these individual terms, if they do not go to 0, then the series diverges. Be very careful about something here. When we're looking at convergence of a series, kind of like the direct attack, using the definition of convergence of a series, we're looking at partial sums. This sequence Sn is like 1/2 for the first element, 1/2 plus 1/4 for the second element. It's the sum of two things for its second element. For its third element, it's the sum of three things, and so on. For the test for divergence, or the divergence criterion, we're looking at each individual term. We're essentially coming back here and considering the terms of the series, A1, A2, A3, A4, almost as if we're like plucking out those terms and turning them into elements of a sequence. So if the individual terms do not go to 0, then the series diverges. An important note, this does not work the other way. In other words, if I look at the individual terms and see that they go to 0, that does not necessarily mean that the series converges. In fact, there's a very famous example, the harmonic series, 1/2, or well, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Those terms clearly do go to 0. 1/2, 1/3, 1/4, 1/5 is going to 0. But that harmonic series does not converge. So more formally, we would say that the individual terms going to 0 is a necessary condition for convergence. It has to be true in order for convergence to occur, but it's not sufficient. Just knowing that it's true is not enough to show convergence. So two notes here. One is this is a necessary but not sufficient condition for convergence. And the second is that we're looking at each term in the series. Whereas the kind of direct attack on convergence using the definition is looking at the sequence of partial sums. So the first term, and then the sum of the first two terms, and then the sum of the first three terms, and then the sum of the first four terms, and so on. Are you starting to see why the whole sequences and series are so so easy to get confused here, right? Here we're looking at sequence of partial sums, which are kind of like partial series, and then here we're looking at something that feels much more like a sequence, like do the AIs go to 0 or not? Do the individual terms go to 0? As a corollary, the contrapositive, of course, is true. If A, then B, the contrapositive is if not B, then not A. If the series converges, in other words, if it does not diverge, then AI goes to 0. In other words, it does not go to 0. For any convergent series, the individual terms must go to 0. Right. Now, again, like we look at the sequence of partial sums, the sequence of partial sums is going to 1, but the individual terms, 1/2, 1/4, 1/8, 1/16, these individual terms are going to 0. The sequence of partial sums is going to 1, but the sequence consisting of just the terms, 1/2 for the first element, 1/4 for the second element, 1/8 for the third element, that sequence of the terms themselves is going to 0. I'm trying to say each of these statements that I make, at least twice in two slightly different ways, so that hopefully that gives you a little bit of a different perspective. I know it's a lot to keep track of. It sounds like we're, I don't know, that we've made our way into a law class or something like that. You're like, wait, didn't she just use that word in a different way? And what does everything mean here, right? It's one of those things you have to go through it a few times to keep everything sorted out. Okay, so that for the proof of the original theorem, the test for divergence, we're going to prove the corollary, the contrapositive. If we prove the contrapositive has the same truth value as the original statement. If A, then B, or if not B, then not A, have the same truth value. So we can get away with proving the contrapositive, and that proves, just under the rules of basic propositional logic, that the original statement must be true. So we'll prove that if the series converges, then the limit of the terms is 0. So suppose that some AI converges, then some AI is the limit of the sequence of partial sums, Sn, by definition. And we also know that the limit of the sequence is a real number L. That's what it means for our series to converge. But we notice that the limit as n goes to infinity of Sn, of the nth partial sum, is the same as the limit as n goes to infinity of the n minus first partial sum. The nth and the n minus first partial sums themselves are not the same for a specific n, right? The third partial sum is not the same as the second partial sum. But if I make a list of like all of the partial sums, let me, can I pick a different color up here? Yeah. If I make a list of all of these partial sums, this will be like the n bit, and I look at this sequence, 1/2, 1/3, 1/2, 3/4, 7/8, 15/16, 31 30-seconds, and so on. Well, then the n minus 1, if I'm off by 1, so this will be so if this is n equals 1, then n minus 1 is 0. Let me make this one n minus 1, and then this one n. So then I have 3/4, 7/8, 15/16, 31 30-seconds, and so on, right? So if I pick a certain element, if I'm the fourth element in, those are different numbers for the two sequences, but I notice that if one of the sequences goes to 1, then the other one goes to 1 as well, right? I hope that's clear. The convergence only cares about the tail, about when we're way off going out towards infinity. It doesn't really care about whether we've chopped a couple of pieces off at the beginning or something like that. Keep in mind, we're in the sequence of partial sums. So this one is like, A1 plus A2 plus A3 plus A4. And this one is like, what, A1 plus A2 plus A3 plus A4 plus A5. We're not chopping off terms from the beginning of the sum. We're just chopping off partial sums from the beginning. And right, we still have like all of our terms in each one of these. It's just that we're not going out quite as far at the same element number. So the limit of the sequence of partial sums Sn, if that limit is L, that has to be the same limit for Sn minus 1 if I just re-index things. But Sn is just Sn minus 1 plus An. So this tells me that, and the limit of the sum is the sum of the limit. So this tells me that the limit n goes to infinity Sn minus 1 plus the limit of an. But wait, limit Sn minus 1 is just L. So this must be L plus the limit an, and that has to equal L. So L equals L plus something. That thing has to be 0. So limit an has to be 0. Just based on the series converging, what that means, and then just re-indexing this partial sum by 1 and recognizing that has to have the same limit. Right? And in other words, the effect of like leaving off one term at the end has to become negligible as we get far out in the sequence of partial sums. So that term at the end, that an, has to go to 0. So for example, the series sum I equals 1 to infinity of 1 over 2 to the I converges as we kind of intuited above. Therefore, 1 over 2 to the I has to go to 0. And we see that that's indeed true. Or on the other hand, we can look at the series sum I equals 1 to infinity of 1 plus I over 1 plus 2I. And here I actually notice that the individual terms, as I gets large, these go to 1/2, right? 1 plus x over 1 plus 2x, like something like that. Basically the ones become negligible and the i's divide out then. So this goes to 1/2. That's not equal to 0. Since the individual terms do not go to 0, this series diverges. And that kind of makes sense because because when I'm far out in the tail, my series basically consists of adding essentially 1/2 to itself a whole bunch of times. And certainly if I just add 1/2 to itself forever, that's going to blow up that sum. So as I mentioned here, be very careful to keep in mind whether you're talking about convergence of a sequence, whether you're looking at the individual terms inside the series, or whether you're talking about convergence of a series, whether you're looking at the sum of the terms overall and things like sequence of partial sums. These are different ideas. They share some similarities in, in their terminology and so on. They operate side by side. They're related, but they're different ideas. Okay, so let's look at perhaps the most important series, the geometric series. So consider the series. Now here we're going to start with I equals 0. It makes things work out a little bit nicer, but consider the series sum I equals 0 to infinity of r to the I. And here r is a real number. We expect that for some values of r, the series will converge. For instance, when r equals 1/2, we expect it to converge to 1. And, well, more or less 1. I should be a little careful because I started this series up here, I equals 1 and not I equals 0. So, but we'd expect it to converge when r equals 1/2, maybe not for some other values of r. Can we figure out for what values of r is the series convergent? Well, let's try a couple of cases first. A pretty good one to try is r equals 0. Let's say what we mean by this. We mean 1 plus r squared plus r cubed, and so on. If I try r equals 0, what is my sequence of partial sums? Well, my first partial sum is just my first element, 1. My next partial sum is 1 plus 0, or 1. My next element in my partial sum, S3, is 1 plus 0 plus 0, or 1. I see this sequence of partial sums converges to 1. So for r equals 0, this should converge. It should converge to 1. What about for something like r equals 2? I can look at this like maybe directly if I really wanted to beat a dead horse. S1, or I suppose we could call it S0, is 1. Our first partial sum to show up is just this first term, 1. Our next is 1 plus r, 1 plus 2, or 3. And then we have 1 plus 2 plus 4, so 7. And then 1 plus 2 plus 4 plus 8, so 7 and 8 is 15. I think this is going to be like 2 to the n minus 1, something like that. But I pretty clearly see that this is going to go to infinity. And in fact, I could even do something a little more elegant. I see if r equals 2, I'm looking at the sum I equals 0 to infinity of 2 to the I power. And I can ask, do the individual terms, now we're not talking about the sequence of partial sums anymore. We already looked at through the lens of the sequence of partial sums. We say, yeah, we think it diverges, but could we do things a little more elegantly and come to the same conclusion? If I look at the individual terms, 2 to the I, as I goes to infinity, this goes to infinity, not 0. So by test for divergence, this diverges, right? If the individual terms do not go to 0, then the series diverges. We're just applying that test there. For something like maybe r equals -1, it's kind of an interesting one, right? Let's kind of write out our series, what it would look like. Well, we have, so sum I equals 0 to infinity of -1 to the I equals, maybe I'll kind of put this in quotations. Well, my first term is just 1, so just 1 plus, and then r, or that's just -1, plus r squared, well, that's +1, plus r cubed, that's -1, and so on. Now be careful here. My sequence of partial sums, my sequence Sn, I start by just plucking out my first term, 1. And then I add my first 2. 1 plus -1 is 0. I add my first 3, and I get 1. Add my first 4, I get 0. 1, 0, and so on. Now, some people look at this and say this feels like it doesn't diverge in the same way that something like this diverges. It feels like r equals 2 like really diverges, and r equals -1, it just kind of like flips back and forth, but kind of stays in the same ballpark. So, particularly in fields like maybe physics, where they're looking to solve a particular problem in a particular way, they might try to say something like, maybe like look at the nth partial sum divided by n or something and see what happens there. But we're not doing that here. That's not what our definition says. So there are different modes of convergence and so on. Like this like really diverges, but this like kind of diverges maybe in some loose sense. But we're not, we just have a definition. Does it converge? Does it diverge? Does a thing that keeps flipping back and forth between 1 and 0, does it have a limit? No, it does not. Diverges. The limit n goes to infinity of Sn doesn't exist. And analogously, I could, just like I did up here, I could look at my individual terms. So I've looked at this through the lens of the sequence of partial sums already and found out it diverged. Is that consistent with my test for divergence? I could look at my individual terms, r to the I, or -1 to the I. These individual terms look like uh, plus 1, minus 1, plus 1, minus 1, and so on, this limit I goes to infinity, a sub I does not exist because it keeps flipping back and forth between plus 1 and minus 1. So by the test for divergence, this diverges. The series diverges because the individual terms don't even have a limit, let alone have a limit of 0. So for each of these last two, I kind of showed through the lens of the sequence of partial sums, and then we looked through the lens of the individual terms in the test for divergence. We took two different perspectives to show the same thing in each case, just to be clear about what I did. It would have been perfectly fine to just do one and not do the other one. That would have been a perfectly valid proof, but in this case, I just wanted to show it through both lenses. Okay, so maybe we have enough to go on here. So the first thing we might want to ask, so case one in some sense, when does r to the I go to 0? Now, if r to the I goes to 0, that's not necessarily enough to prove convergence of the series. But if r to the I does not go to 0, then I can exclude any of those r's. So maybe I can even say, when does r to the I not go to 0? And the idea being that then these r's cannot lead to convergence. In other words, when does r to the I power, when does 1 r squared, r cubed, and so on not go to 0? Well, that's any time that absolute r is bigger than or equal to 1. So we can kind of flip this around and we can say something like, if absolute r is bigger than or equal to 1, sum I equals 0 to infinity, r to the I diverges by the test for divergence. So at this point, really our only hope for convergence is for some r's, perhaps all r's, that are strictly less than 1 in absolute value. I mean, we saw r equals 0 fits that criterion and happened to converge, but we can't necessarily conclude at this point that all r's with absolute value less than 1 do converge. We have to do a little more work. So this was kind of the first thing we can exclude is all of the r's bigger than or equal to 1 in absolute value. Okay, so what about the r is less than 1 in absolute value? So let's take absolute r to be less than 1. And here we're trying to prove convergence. We're kind of guessing that at least some of these r's will lead to a convergent series. If we're trying to prove convergence, we can't just look at the individual terms. That's kind of how we attempt to prove divergence. If we think the thing blows up or diverges, then we might look at the individual terms and see if we can get that result pretty easily. But to analyze convergence, we need to analyze the sequence of partial sums. Okay, so let's look at the sequence of partial sums. So this is the series that we're working with. And the nth partial sum, Sn, is 1 plus r squared, and so on, plus r to the n power. That's our nth partial sum. Okay. Now there's kind of a famous little trick that we can do here. We can consider, now note that this is finite, triple exclamation point. So we can do all kinds of stuff to this. Anything that is valid, from math 80 or 90 up through now, we can do to this. We're not, we have to be very careful when we try to do some kind of algebraic manipulations on the series on an infinitely long sum. We don't really know how algebra works there. We don't have theorems to say how that works. But for Sn, this is just the sum of n. Maybe n is 10, maybe n is 100 million. Regardless, it's just the sum of a finite number of things. All of our good old algebra works here. So I can factor things out. I can use the commutative property. I can rearrange things. No problems here because this is just a finite sum. The same kind of thing that we would deal with in Math 90 or Math 108 or something. So I could, for instance, multiply this by r. If I multiply Sn by r, the 1 gets multiplied by r to make an r. The r gets multiplied by r to make an r squared. The r squared to make an r cubed. The r to the n minus 1 to make an rn, or r to the n. And the r to the n gets multiplied by r to make an r to the n plus 1 power. And I think to myself, boy, it would be nice if a whole lot of stuff would cancel out. So if I put a minus here, and I add these together. Why can I do all of this? Why am I being so flippant about doing all these operations? Because this is just a finite sum. It's just a bunch of things added together, not infinitely many things. If I was trying to do all of this like inside of the series, so to speak, this would be much more questionable. I would have to justify every one of these steps. But because I'm in the finite partial sum, I can do anything I want. I mean, not anything I want, anything that's valid algebra, that we've learned up till now. So this is 1 minus r times Sn on the left side, just factoring the Sn out. And on the right side, I have 1. That doesn't have anybody to cancel it out. Plus r has a minus r, plus r squared has a minus r squared. These all go away. Up through the plus rn has a minus r, plus r to the n has a minus r to the n that came from the r to the n minus 1 in the black sequence, or the black sum. But then we have a minus r to the n minus 1 power that doesn't have anybody to cancel it out. So we have this one left over from the black partial sum, and this one left over from when we multiplied that by r and subtracted. Or I see I get a formula for Sn, the nth partial sum. It's 1 minus r to the power n minus 1 over 1 minus r. Keep in mind that absolute r is less than 1, so r is in open negative 1 to 1. No issues with that 1 minus r in the bottom there. We're staying away from r equals 1. And my nth partial sum, what does this go to as n goes to infinity? Well, that's really just a question of, that's 1 over 1 minus r times 1 minus the limit n goes to infinity of r to the n minus 1. And here r is a number that's between negative 1 and 1 strictly. But if I take a number strictly between negative 1 and 1, raise it to a power and make that power bigger and bigger, this is 0. I suppose this is what Sn equals, not what it goes to. No, I had that right. That was right. And now I want to say Sn goes to as n goes to infinity, 1 over 1 minus r, if absolute r less than 1. So for what values of r is the series convergent? Converges if absolute R is less than 1, and diverges otherwise, and it converges to 1 over 1 minus R. We kind of got this for free. We actually know the sum of any convergent geometric series now just by using this formula. That doesn't happen often, so it works out very nicely here. When R equals 0, if I plug that in here, that is less than 1 in absolute value, so it should converge. What should it converge to? 1 over 1 minus 0. That's just 1 over 1, or should converge to 1, and that's exactly what we found here. What if R is 1/2, like up here? If R equals 1/2, we converge to 1 over 1 minus 1/2, or 2. Now, why is it 2 and not 1? Well, because we start at I equals 0 here, right? We have 1 plus 1/2 plus 1/4 plus 1/8. And up here, we started at I equals 1, so we don't have the 1 plus. So this converges to 1 instead of 1 plus 1, or 2. We just lost that first term. So losing this first term was consequential. Starting the sum at 1 instead of 0 was consequential. We have to keep in mind that the indexing, sometimes that's important. As a little side note, if I plug in R equals 1, that's kind of like frowny face. I get 1 over 1 minus 1, 1 over 0. What do I do with that? R equals 1 would be like adding 1 to itself infinitely many times. That's kind of like feels like it should be really not convergent. But R equals -1 is what we have here that kind of didn't feel quite as not convergent. What if I just, no, I'm not allowed to do this, which is why I'm kind of writing it in red over here. But what if I reimagined my definitions? What if I chose to work under a different set of definitions? What is 1 over 1 minus -1? That's like 1 over 1 plus 1 is 1/2. Kind of interesting that it turns out to be 1/2. My sequence of partial sums is jumping back and forth between 1 and 0, and 1/2 is like right in between those. Right? So again, you might find a YouTube video where they say, oh, well, we got this formula and we can kind of just plug in R equals -1. In our course, no, we can't. We're working under this specific definition. But there are other definitions that kind of expand the idea of convergence, the notion of convergence, to essentially allow more series to be considered convergent under these different definitions. But those are different definitions. They'll lead to different consequences and different conclusions and different things that are or are not allowed. So it's a different framework. So on one hand, this like seems plausible that maybe R equals -1 could kind of plausibly under a different set of definitions lead to convergence. Not here, but that might happen in a different case. So that is the geometric series. We also note that we have a formula for the nth partial sum of a geometric series. There are lots of applications of geometric series proper, and there are also lots of applications that deal with the kind of geometric sum, like an nth partial sum of a geometric series, particularly things like mortgage, right? If you want to figure out like what your payment should be for this present or this amount of a mortgage over this term at this interest rate and so on, at some point you're going to have something like this, 1 minus something to the n minus 1 over 1 minus something pop up in your calculation. I want to issue a little bit of a warning because at this point we might become complacent and think, okay, I've done all of this in the partial sum. Well, why don't I just do it in the original series? Not the Star Trek original series, but why don't I just do that up here in this infinitely long list? What difference does it make, right? Let's take a look. Let's try to do something like that. I could write 0. 0 is very clearly the sum of infinitely many zeros, right? I could certainly write sum I equals 1 to infinity of 0. That's clearly going to be 0. I add up the first 0, it's 0. The second partial sum, 0 plus 0 is 0. The third partial sum, 0 plus 0 plus 0 is 0. Very clearly, that series is going to be 0. That's all I've written here in this first line. There's no question in this first line. But then within the series symbol, I equals 1 to infinity of, I can write 0. Instead of writing 0 for each term, I could write 1 minus 1. So this is valid, and there's nothing wrong with this. I just changed each of my zeros to 1 minus 1. Now I say, well, commutativity is nice, associativity is nice. Let me just regroup my my bits down here. Instead of 1 minus 1 plus 1 minus 1, I'm going to do 1 plus negative 1 plus 1 plus negative 1 plus 1, and so on forever. There's always going to be another plus 1 to counteract the negative 1 because I have infinitely many of them. So this is going to be, well, this negative 1 plus 1 can turn into a 0. And this negative 1 plus 1 can turn into a 0. So there's nothing wrong with this equal sign. But then I have basically 1 plus this series. But that's 1 plus 0 or 1. There's nothing wrong here either. So the issue must have been here. All that I did was use the associative property. It's like one of our most basic properties, right? But because I used it in the infinite series, I ended up with 0 equals 1, which pretty clearly is not true. Something as simple as using an associative property, just not even rearranging terms or anything like that, just shifting how you're grouping terms together in an infinite series, it can cause, something like this to happen, right? So we have to be very, very careful about what we do within the series. However, again, once we pass to the partial sum, we can do all this no problem. If I was considering a partial sum here, and I had 1 minus 1 plus 1 minus 1 plus, and let's just do like the third partial sum, 1 minus 1, and I tried to regroup, I have 1 plus negative 1 plus 1. So I use that one, this one, and that one, plus negative 1 plus 1, this one, and that one, and then plus negative 1. These can turn into zeros, but I always have to resolve the first and the last term, and they're always going to resolve back to 0. So again, I can do all of the basic arithmetic and algebra stuff that I want to inside of the partial sum, because at that point it's just a finite sum. I really want to be careful what I do inside, so to speak, of the series as a whole, because as I've just demonstrated here, like even something as simple as using just an associative property can really mislead you. So that is where we're going to leave it today.